Hi everyone. Today is a continuation of the lecture series on the fundamentals of orbital rocketry. This is part 2. If you haven't seen part 1 yet, go down to the description and click the link. If you want to see part 3, it's also in the description. So there we go. But without any hesitation, let's get right into it. So these are two different ways to look at the ideal rocket equation. You have the more traditional format, which takes the effective exhaust velocity and relates to the starting total mass and the final total mass. And you have the somewhat untraditional version that relates the ratio of the delta V and the effective exhaust velocity raised to the power of E to the overall mass ratio of the rocket. And as I said, this really does work. This is really how rockets function. You can define how their velocity changes based off these two equations in some way, shape, or form. But there's a very big problem with this. So that rockets are not just their starting total mass, their starting total mass and their final total mass. There's so much more than that. But you have to think about a rocket. What is it? It's a payload of some kind with a propellant tank, and I'm grossly oversimplifying here. Propellant tank and maybe an engine on the end. This is a great drawing. The problem is that your final total mass of your rocket isn't just the mass of your payload, which is what some people who first look at this may originally interpret it as. Your final total mass is the payload plus the mass of your tankage plus the mass of your engine and whatever propellant residuals you may have in your propellant tanks. These are all real-world considerations that you have to make when you're dealing with trying to design a rocket of any kind, because, well, you need something to store your propellant in, and you can't burn all of your propellant. There's a couple specific reasons for this. In liquid rockets, you can't do it because there are very sensitive turbo pumps in the engine. And generally speaking, when you're playing with fluids, gases and fluids don't really like to mix that much in the same system. So you can run into a situation where you're feeding propellant into the tanks and you try to drain it to empty, you get a gas bubble, it blows up the engine, no space for you. So you have to consider all of these factors, the mass of the payload, the mass of the tankage, and the mass of the engine when you're dealing with this. And at first it might seem really challenging because the mass of your tankage is obviously a function of how much propellant you have available. It's kind of like looking at a water bottle or looking at a soda can. A soda can is a really common example because it's very similar in characteristics to how we build rockets. So what we play with is a term called the propellant mass fraction, or PMF. And this is a dimensionless term. It's a ratio. It doesn't really have any real-world considerations except for the fact that it's a ratio. And this is defined as the mass of the propellant over the total mass of the stage. And generally speaking, what do we expect in this? We expect numbers in the 0.8 to the 0.96 range for this. And this is especially for liquid rockets. Liquid rockets, you can get away with a lighter propellant mass fraction because, in a sense, you're not just dealing with solid motors, I should say. The entire casing has to bear the thrust the engine produced, whereas with liquid motors, it's just the engine that has to deal with that. So you can get a much lighter tankage. You can basically have almost a gossamer thin propellant tanks. And there are rockets, even in the world today, that still use very, very thin and lightweight propellant tanks. Those are called balloon tanks. The Centaur upper stage that's used to this day, when it burns liquid oxygen, liquid hydrogen, uses a propellant tank of that nature. It's basically just a large stainless steel balloon. It's pressure stabilized. If you take out the pressure, the whole thing collapses. We're not going to be playing with this so much because we mostly are focusing on solid rockets. We still have to make the same general consideration. And thereabouts as what we're looking at solid-wise is probably a number of about 0.86. This is a number that I've come to after doing a lot of research into this question and comparing other solid rockets to one another and coming up with a general average. But there's also a little caveat to this, and this caveat has to do with scaling. So the problem is that it's not really a linear scaling when you're dealing with a pressure vessel. You think about it like this. The size of your pressure vessel generally means a much heavier one for a much smaller volume, so your efficiency looks something like this. It kind of behaves linearly when you're dealing with very large volumes, but not so much when you're playing with the small stuff, and we're kind of playing with the small stuff. So that's why you could look at this number, you go off and you can look at commercially available solid motors, and you get a number of like 0.5 or less, because they're smaller. They're a little more mass inefficient. They have to, you have to constrain that pressure with a heavier pressure vessel. So for our considerations, though, this is generally about the domain that we're going to be playing in. So we have to account for this now in the rocket equation. And there are a couple clever ways we can deal with this, but I prefer the simplest, most straightforward way of doing it, which is simply just looking at it. How's it looking? Okay, that's not too bad. Which is simply just looking at it from the perspective of the inert mass fraction, or IMF for short. And that's just 1 minus the propellant mass fraction. So what we can do now is we can take this number, or these values, for whatever rocket we're playing with. In this case, let's assume we got 0.6. We can take this number, we can come up with the inert mass fraction, which is just the complement of that, so that would be 0.140. And now, we go back to the rocket equation. The rocket equation is delta V equal to VE natural log of m sub 0 over m sub 1. And what do m sub 0 and m sub 0, starting total mass, is, as I have written here, the mass of the propellant plus the mass of the inert plus the mass of the payload. And then m sub 1 is everything that's not burned. And we're going to actually lump the inert mass in with propellant residuals and such. We're going to consider that as part of the inert mass. It's something that does not directly contribute to propulsion. So it doesn't directly contribute to propulsion. And of course, the final total mass is just the inert mass plus the mass of the payload. So that is our general setup. Now, we can look at this in such a way that eraser just doesn't work well, does it? We can look at this in such a way that we can start to constrain these terms. Because these are all kind of sort of unrelated, but we recognize that we have the propellant mass fraction and the inert mass fraction of the stage available to us. So we can actually define two of these terms with respect to the same term. In fact, we can look at the mass of the propellant and the mass of the inert, and we can combine it to a new factor called the mass of the stage. And then, of course, what is the inert mass as a function of the whole stage? The inert mass fraction. So all of this becomes then is the inert mass fraction times the mass of the stage. So now we have successfully constrained our variables such that we can actually look at these numbers and we can condense it down to something that's a little more easy to potentially work with. And in fact, we're going to. Let's hope this eraser works this time. Jesus. That's better. There we go. So recalling that, we're going to rewrite the rocket equation and then play with it from there. I really got to push hard to get this to scrub off. I don't know why the hell these are so blah. So let's rewrite the rocket equation with this new consideration in mind. Thusly, we have delta V natural log of our mass stage plus the mass payload over IMF as mass of the stage plus so that is what we're looking at from a high level here, knowing our constraints of our inert mass fraction and our payload mass. The thing we have to consider next is that, very importantly, well, actually I should think about this another way. I should probably represent this a little more visually for you guys. The mass of the stage is everything in the stage by itself. The inert mass is mass of the tankage, residuals, plumbing, propellant, everything that's not burned up but still part of that stage and a function of the total mass of that stage. And there's the payload, which is what we actually care about. It's the satellite or it's another upper stage of the rocket. Now, you'll recognize that the next step here, because, well, this only tells us their delta V. If we're trying to go backwards, we're trying to say we have a certain payload, and we want to know what kind of stage we need to back up that payload and get it to that delta V, we have to use the other form of the rocket equation. So we have to rewrite this as E delta V over VE is equal to this whole function. And I'm not going to bother rewriting it because it's really annoying to do. So that is the setup to our problem. Is we now have this setup, which plain and simple is and now we have to solve for the mass of the stage. Because that's our consideration, that is our setup problem here, is that we want to determine for a given payload mass, which is what we can totally control, given our delta V and our effective exhaust velocity, all factors that we know or we can calculate or we can approximate, we need to put those terms in and come up with reasonable numbers for our stages, with the realistic consideration of the stages themselves having inert mass to come with them. So we can rearrange this very simply. It's just a little bit of algebra here and there. And all we do, I'm actually going to change the variables a little bit. We're going to call this R. This whole value will be called R. Just means it's a little easier to play with and it's not me rewriting the same thing 20 times. So that means that the first thing we can do, we take the denominator here and multiply it by R. So we come up with this little equation as our starting point. And we get R is equal to, I have it in my notes, actually no, because it's multiplied by, R is then multiplied by the product of M payload plus IMF times mass stage is then equal to our mass payload plus mass stage. So then what we do is our next step is we can distribute everything. We distribute R to this. We get R, M plus M plus R, I, M, F. So our next step, we can rearrange this. We distribute after these things. We have M payload, M stage. Everything's all nice and relatively happily separated. Now the next step we can do is we can put everything on the same side. We want all the mass payload on one side. We want all of our mass stage on the other side. So that looks something like this. Payload is equal to M stage minus RIMF M stage. That looks really ugly, but this is only like 4 terms that we're playing with. I'm just being very verbose and identifying them so that way we all don't go insane trying to figure that out. And the final step in this is we can factor out M payload on this side, so we get R minus 1 times M payload is equal to, thus, very simply, 1 minus R times the inert mass fraction, RIMF. Probably this is my parentheses there, times M stage. And then the final step in this entire process, we can simply take this and put this under that. And that yields the final version of this equation that we're playing with here, where you're writing everything in terms that we can define the mass of a stage for a given delta V with the inputs of our propellant mass fraction and all these other factors. We can finally come up with the final form of this, which goes very simply over 1 that's it. This simple definition, of course, well, I have to track in R is equal to E delta V over V. This simple definition is really the starting point for trying to design basically almost any launch vehicle really starts with this consideration. Knowing from previous research what the inert mass fraction of your stage is probably going to look like, knowing your target delta V and your effective exhaust velocity, knowing how much payload you need, you can immediately take this and you can start doing things with it. And that is really, really powerful. So the question, of course, then is, what do we do with this? We got our delta V. I talked a little bit about the delta V in the previous lecture, about how delta V getting to low Earth orbit. But what do we actually do with this? How do we go from that to that? How do we partition our delta V? And that's a very technical term, but that's exactly the word that we use, is partitioning. Because we can't reach space in a single stage. Actually, I put a big asterisk on that. There are conditions in which you can do it. The problem is those conditions are very specific, but for our purposes, for a solid an all-solid launch vehicle, because it's the simplest thing to consider from an engineering perspective, we can't reach space in a single stage. So we have to split it up. We have to stage. And why does staging even become efficient? And oh man, this is a lot of stuff for you guys to look at, but I'll try and parse it down a little tiny bit. But the fundamental principle that I found, or at least something that I've discovered in my own work, and I'm 90% sure this is an actual thing, is to optimize your vehicle, you basically want to build the smallest possible vehicle for a given job. Because everything that goes into the total mass of the thing is in some way, shape, or form a direct function of cost. In fact, I found that in some research I've done on my own time, that you can actually almost directly predict the cost of a launch vehicle by approximating taking its inert mass and multiplying it by $4,000. And that will generally, as a rule of thumb, give you a good impression of how much it will cost to build an orbital rocket. So, for example, we have something like the Falcon 9 first stage. Now, Falcon 9 is a little bit of an exception to this rule because it doesn't quite play by it, but as a general ballpark of it, the inert mass of the Falcon 9's first stage is 22 tons. So you can ballpark that as being maybe about 80 million to produce or manufacture. Realistically, we know it's not entirely the case. Actually, I think it's closer to 2,000. I think it's close to 2,000. Yeah.
Are you talking about kilograms?
Yeah, kilograms.
Okay.
Kilograms for it's about like
4,000.
It's about $4,000. Roughly is a ballpark $4,000 per kilogram. Some situations it doesn't work, but it is roughly speaking almost completely true for almost all launch vehicles any size class. Even SLS has a cost of about $4,000 per kilogram. Again, there are exceptions. Like I said, Falcon 9 is a little bit of an exception because it's built almost entirely in-house, or they don't really contract out a lot, so the cost is a little bit lower. We've had quoted numbers of $25 million for the stage, which is a lot closer to $1,000 per kilogram. But if what we're playing with here, it's probably a really safe estimate to say, okay, it's going to be about this much. Solids are a little bit of an exception to this rule too, because generally speaking, solid motors have to come with propellant pre-installed. And that's not really cheap because you got to consider hazmat and other real-world shipping considerations. But for the most part, you can put the rule of thumb in your head and use that as a proxy for the total cost. But yeah, there's a very strong correlation between how much a rocket weighs and how much it costs to build. So you want the lightest possible rocket for your given mission because that'll save you the most money. And how do we do that but with staging? There is a very long derivation that I have on my notes here that I won't get into because it would literally take me about 20 to 30 minutes just to write out all the numbers. But what I basically did is I looked at a scenario for a very simple launch vehicle with a total delta V, like a target delta V of 9,000 meters per second, which is within reason of what we expected when we talked about getting to orbit in the last lecture. We got about 8,800 something. I didn't write it down because I'm stupid, but we got about 8,800 something. We use that as a fallback. Now the question is how do you divide this up? How do you say, okay, we got 9,000 meters per second of this pie. What do we do with it? And the most efficient way that I found to do it in my own research and has been backed up by experimental testing in this and simulations is you partition it as a function of propellant mass fraction and the specific impulse. Because you want to give more of your delta V to stages with higher specific impulses to reduce the total mass because it's better performance for a given amount of mass you have available. You also want to constrain it based off of your propellant mass fraction because your propellant mass fraction, well, that determines how efficient your rocket is at holding propellant. If you have a stage that has a very high specific impulse but a very low PMF, you don't want to optimize your entire rocket for that because that's not really great. And in fact, that is the case when it comes to a lot of rockets, especially ones that have liquid oxygen, liquid hydrogen upper stages. So you have to make that consideration. But, big asterisk, You can actually, if you assume that each stage is the same propellant mass fraction and the same specific impulse, you can effectively treat it as a 1-to-1-to-1 ratio across your entire rocket. In other words, all the stages have the same delta V. And for our purposes, for the first round approximation that we're talking about here for the launch vehicle, we are going to treat it in that way because it's the most reasonable way to treat it based off of what we know of experience. Now, there are caveats to this. One of the big ones is that specific impulse that changes with altitude. Rocket engines burning in space can get a higher effective exhaust velocity because there's no gas pressing on the inside of the bell to resist the propellant coming out, so you get a little higher performance. That's generally true. You have to make engineering considerations for that as well. But as a approximation, we can generally use a nice round number between the sea level specific impulse in atmosphere and the vacuum specific impulse. There are calculations that exist that rely on the vacuum specific impulse, but that's a special case and that's a special setup, and I'll get into that very end of this lecture. Yes.
So when you say 1-to-1-to-1 PMF to
Oh no, this is 1-to-1-to-1 for the delta V in the stages.
For the other stages.
Yeah. So in this, for a 3-stage rocket, that means that each stage has a delta V of 3,000 meters per second.
Okay. And that doesn't apply necessarily that they would be the same size, right?
Correct. Very good point. They don't have to be the same size. They actually vary in size. And when I talk about the derivations here, I will actually show that very, very, very nicely, I think. So we can take this, and I'm going to simplify this down because, like I said, I got an entire page of notes here that I have to parse out. I'm not going to parse it out on the board because I don't want to make you guys go insane. So I'll put it very simply. I looked at a scenario for this input, which was delta V of 9,000 meters per second, a specific impulse of 300 seconds, which translates to a effective exhaust velocity of 2,980, I think, right? Yeah, 2,943, I'm close. And then a propellant mass fraction, which is a little bit higher than what we're actually going to be expecting in this rocket, but I use this because it's just a nice round number and it's easy for me to play with in a notebook. 0.9. And with those considerations in mind, taking a look at this, we can of course derive the inert mass fraction, which is 0.1, because it has to add up to 100. And I ran through 3 different scenarios with a 2-stage rocket, a 3-stage rocket, and a 4-stage rocket. Obviously, 1 stage is kind of impossible to do, so we won't really worry about that. So, 2-stage rocket. I started with an input mass of 1 kilogram, and then worked my way progressively through each stage. Is it realistic? No, we'll talk about some of the deeper considerations of this in the next part of this lecture, but basically the total mass of the first rocket was 47.2, I'm going to say 0.25 kilograms. That's with payload, that's with everything else all accounted for. 3-stage rocket had a total mass of 41.07. And the 4-stage rocket had a total mass of 36.51 kilograms with these inputs. So you can kind of see where staging becomes important, because you can take the mass of your rocket, and by adding more stages, you can start bringing it down to a lower and lower number. And this isn't linear. This is very much a situation where you have diminishing returns. Like your maximum takeoff weight as a function of your stages kind of looks something like this. And of course, you approach infinite complexity at that point. Every stage is now a new point of failure, which is something we'll talk about in the next part of this lecture as well. So you have to kind of strike the balance between, number of stages and how many points of failure you have and how good is your overall mass. And look how improved it is between 2 stages and 4 stages. Not as much between 3 and 4 though. So the reliability, actually, I calculated this as a very straight, simple thing, and you can find the reliability of this is about 98%. If each stage is 99% reliable, this is 98, this is 97, this is 96. So you can kind of start to see how it decreases a little bit because every new stage is it becomes a new complex point in the whole system. So that's generally an idea of the benefits of staging, being able to use the derivation the little equation I talked about earlier in a realistic context. And we'll actually walk through the calculations for that to summarize this section of the lecture. Because we're actually going to take a look at a hypothetical scenario of what if we wanted to launch 20 kilograms into space. It's quite a bit. That's about 40 pounds. But we're actually going to sit down and we're going to walk through every step. So now we're going to be looking at an actual, somewhat realistic scenario, which is almost completely sufficient for a first round approximation. And we're going to see if we can get 20 kilograms of mass. What it would take to get 20 kilograms of mass into low Earth orbit with a 3-stage rocket. Let me just prepare my notes here real fast. And we have the following inputs. We have a total delta V of 990. We have an effective exhaust velocity of 2,943 meters per second. We have a propellant mass fraction of 0.6. And an inert mass fraction of 0.140. And we are shooting for 3 stages. And we have a payload, a starting payload, of 20 kilograms. So, let's walk through this. So, our first stop on this is dealing with the last stage on the rocket, the smallest part of the rocket that provides that last kick into orbit. Now, the reason why I chose 9,980 meters per second is because this is actually from a simulation that I ran, and that factors in gravity losses and aerodynamic losses into this calculation. So we're going to play with that as our starting point because it'll give us the extra margin we need to make sure this thing definitely works. So we start off with our first stage, and we recall the equation that we derived to get here, which is as, make sure I'm writing this correctly, I don't want to completely embarrass myself in front of the internet. There it is. Yeah, so we have r minus 1 and payload over 1 minus INFR. So this is our starting point in this little equation. Now, one nice thing is because we're treating each stage with the same delta V, that means that our R value for the e to the power of delta V will be a constant throughout the entire thing. So we can, of course, really quickly calculate that. And we find that for a 3-stage rocket, and you can whip out your calculators if you want to participate in this part. For a 3-stage rocket, divide that by 3, tell me what delta V has.
Yeah, 3,326.67.
Oh, I'm sorry, I'm 9920. Please forgive me on my slight flub here. Yeah, 9920.
3,306.
Point something?
0.66.
Okay, so we're on the 3307. And that means that E delta V VE then should be a constant value, and you can run that through your calculators if you like. Okay, I do have a value for that. That's correct. That's good. Did write that right. Wonderful.
And do it.
Yeah, e to the power of delta, just for this, take this delta V and use that in that equation.
Okay, this is a new calculator, so give me a sec.
That's fine. Got it? Yep.
Where's the?
It should be on next to the logarithm value.
It's basically
It's the inverse of natural log.
Whatever.
Or 2 point, just you can use 2.7 as a ballpark. Also, I've already written the answer on the board.
2.7 to the 3306.
3307 over 2943.
I got 3.052.
Close enough. Yeah, 3.076. This is what you'd actually get if you chucked in E. Because I know it's 2.714 something. I'm not a mathematician, so our cameraman has to take a call real fast. Or you were in charge of making sure this does not go off. Just wiggle the mouse every couple seconds. Good. Okay, so we have a value of 3.076 for each stage. We have this value, and that means that we can basically use one equation for this entire thing. Because we have the numerator, which is just r minus 1, so that's 2.076 times m payload over 1 minus the inert mass fraction times r. And if anyone wants to run through that, I'll just, spoiler it, I'll just tell you. It is 0.4364. Now we go through our first calculation. Finally do this. Our first payload mass, and I say first payload mass because this is going to come up again and again, is 20 kilograms. So all we do is we just take 20 kilograms and we substitute it in for this. 2.076 times 20 all over 1 minus 0.4364. And that means that we arrive at a stage mass of 72.924 kilograms. Pretty nice and simple. Oh, I'm blocking the view. 72.924 kilograms. And what that basically means is that we have to complete our delta V of 3,307 meters per second. We need to have we're in a stage of that is 86% efficient at holding propellant. We need a stage that is about 73 kilograms in order to back that up, which is, about 150 pounds. So I'm actually going to have a running tally because I wanted to illustrate this point over here. Can you see this part of the board? Yeah, you can see this part of the board. Good. So stage 3 has a mass of 72.924 and you're going to see how each stage actually gets progressively larger in size. So for the same amount of delta V different payloads, because we need to now make a consideration. As I mentioned earlier, the payload for every stage is either the satellite, like the thing we're actually interested in getting to space, or it's the mass of the stage immediately above it, plus that spacecraft. So the payload for the next stage isn't actually just 20 again. It's 20 plus 72.924, which is, of course, 90 at a bit. 92.924. That is the payload mass for our second stage. That is the amount of mass that the stage has to kick forward. That's the amount of mass that that stage has to kick through 3,307 meters per second delta D in order to get that payload where it needs to be for the final phase of the mission. So now we can do that stage 2. So stage 2, we already have our payload for that. I'm going to erase this real fast because we are going to be playing with this. We have a mass of 92 kilograms, so we have 2.076. Again, we use the same equation because we're not changing anything. 2.076 times 92 and some change. What is that change? 94. And we put that over 1 minus 0.4364. And that means we get a payload mass for our next stage of, a stage mass of 201.592 kilograms. So that's 201.592. But we're not done yet, because for the next stage, the final stage in our 3-stage rocket, we have to take this number and add it to the payload of that stage to figure out how much mass the first stage has to push. So we do that. And we find that we get an approximate mass of 294. I was just looking at it, 5 and 6. That is our now new payload mass for the first stage of the rocket that fires. It's taking this much payload behind it. So we take our numbers again for the final time. We recycle. We say, okay, our new payload mass is 2.076 times our payload mass, which is 294.516. And we put that over 1 minus 0.4364. And we arrive at a first stage mass of 1073.864 kilograms. Nice, sweet, and simple. And we can put that up into our running tally. The total mass of our rocket, sitting on the pad, ready to fly, is thus 1,368.38 kilograms. Fully loaded. And that is a nice, short, sweet, simple way to oh no, my chalk broke. This is a tragic day. That means that the mass of our vehicle is now defined with realistic values for a realistic starting point, and we can use this as a first-round approximation when dealing with design and engineering considerations. We now can calculate exactly how much propellant is loaded in each of these stages by taking the propellant mass fraction from before and plugging it back in. And we can calculate the total inert mass of the rocket by adding up the inert mass fraction times all these stages, minus the payload mass in the system, of course, and going from there. That's why this is a really, really important way of looking at it, because you actually start making real-world considerations when you're playing with these numbers. And And this is a system that if you could optimize everything and work out perfectly, would in fact get you a 20-kilogram satellite to low Earth orbit. Pretty cool, huh? So I've been over a bunch of the more mathematical stuff, and I actually want to take a moment and think about and talk about the less math-related things. It still involves math in some way, shape, or form, but this is a little more. This will hurt your brain less. I'll put it that way. Why do rockets look like this? Wow, that's a really bad nose. Why do rockets all kind of look like this? Why do they have fins? Why do they have long, slender objects? Why? It has to do with the aerodynamics. It has to do with the considerations that we make in designing these and ensuring they fly in stable flight. Larger rockets can achieve stability even if they're very unstable by using something called, by actually taking the thrust and vectoring it. If the rocket starts to slip a little bit out of alignment, they can kick the engine the other direction and torque it around, keeping it stable. You can do that little tiny correction, not thousands, but a lot of times per minute, and it means you can fly a really straight flight. For the rockets we're playing with, the solid ones, without the propellant, without the ability to vector the thrust, because it's a very complicated and cost-intensive system, we don't really have that luxury. And this is true even for amateur rocketeers, except for the one that guy, Joe Barnard, the guy that's got like the little circuit board and he's worked on thrust vectoring. It's really cool stuff. I'll just show you after the lecture. But that exception, for the most part, you have to play by the rule of aerodynamics. And it is no coincidence that even the most advanced high-powered rockets, which are very big amateur rockets, smaller than what we're talking about for orbit here, but still really beefy, all kind of harken back to the fundamental principle of an arrow. It's no coincidence. It's because this is a very stable shape. This is a shape that will point in the direction that you chuck it. In this case, you're chucking it by burning an engine out the back, and will be very resistant. Will be very passively stable. You have to do nothing else for it to keep going in that same flight. And you look at an arrow, and you kind of understand the principles that go into building a rocket. There's a very heavy projectile in front. I'm going to use these symbols to indicate center of gravity, or gravity and center of pressure. And there is a very draggy bit of back. Now, this is greatly exaggerated. Realistically speaking, they're probably like here and here in the actual arrow. But it means it's self-correcting. It means that if the arrow goes a little bit out of alignment, in other words, if the arrow is disturbed by a breeze or a bird flying by or what have you, then your arrow will, of course, torque in response to that. But then your center of gravity and center of pressure are no longer aligned in the direction of flight. So it'll want to turn itself back to a stable position. And it will do that. It'll oscillate probably a little bit, but it will remain flying straight because it is automatically self-correcting. The force that you're getting aerodynamically are now offset from your center of gravity, so it torques around that center of gravity. Torques around this, and it rotates. It's self-correcting. It's self-stable. It's a beautiful, simple thing. The rocket's working in the exact same way. You have fins. You have a center of gravity somewhere here and a center of pressure somewhere here, and it stays stable for the exact same reasons. So rockets are designed the exact same way, very similar principles to the arrow. They have draggy surfaces at the back that keep pointing forward, and they have a little bit of mass in the front. And this seems very paradoxical. If you add more mass to a rocket, it will sometimes become more stable and go higher. It's really screwy, right? But that's aerodynamics at play. And it behaves by the exact same principles. If the rocket deviates from its course very slightly, or twists or turns, or gets caught in a little bit of stiff crosswind, it'll keep pointing straight and it'll keep going about as straight as it can possibly go. Now, of course, that is a very general case thing, but there's some specific considerations to make. When we talk about high-power rockets, right, which is what I have a lot of background in, we talk about the calibers of stability. And that is the distance between the center of gravity and the center of pressure divided by the diameter of the rocket. Do I know why it's called this? I'm not entirely sure, and I won't pretend like I know because I didn't think to look that up on Wikipedia before today's lecture. But it's basically a function of how many diameters apart. those 2 points are. And when you're designing a high-powered rocket that, again, has no active control system on board, you're generally shooting for between 2 to 5 calibers of stability when you're designing it. Fortunately, we don't have to do this by hand because there are programs that will do this for you, such as OpenRocket, which is a Java-based 6-degree of freedom simulator that you can actually put together a little silhouette of a rocket in, and it'll calculate for you your center of gravity and your center of pressure. Very nice, sweet, simple, pretty handy. But, of course, with anything, something so simple is not truly that simple because there are caveats. There are major caveats. And one of the most major caveats to this is going past Mach 1. So if you're familiar with drag and how it behaves at very high speeds, you might recognize that the coefficient of drag will go up, basically uptick right around Mach 1 and then kind of level off at some constant beyond that point. In short, things behave really weird when you go transonic. Rockets are, of course, no exception. What you may have is you basically have the situation where the fins become a little bit less efficient at keeping everything stable because the body's a cylinder. You can kind of treat it as its geometric center will be the same as its center of pressure, more or less. The fins become less efficient at speed, so your center of pressure actually pulls forward. And what this means is that if you're flying a rocket, you work really hard to get this thing perfectly stable. You get it within 2 calibers of stability. You got this nice, long, thin rocket. You're going to say, all right, I'm going to go break the sound barrier. It launches. It goes passes through the sound barrier, goes transonic, goes completely unstable and out of control. And this is a problem that plagued aerodynamic people for years when we were trying to deal with, sending a human supersonic, and it's something that rocketeers deal with as a problem because it's not something that's immediately intuitive. It's not something you can easily simulate in your back porch because, you want to simulate the center of pressure in your rocket, you can tie it to a string and whirl it around your head. That's a real thing, but it's a real test. Going supersonic, on the other hand, it's a little harder to try and approximate. Fortunately, again, software is our savior. There is a very, very useful software called RAS Aero that will actually simulate, and it's a very, very good simulator for high speeds. That is a lot of data, though. It will actually simulate the behavior of a rocket at high Mach, and it will tell you how your center of mass and how your center of pressure will shift as you go past the sound barrier. And that means you can actually design for that when you're building your rocket. You can basically have it so that way you maintain that same level of stability even after you go supersonic. And this is something that, for our purposes, we're talking about for an orbit-capable rocket is one that uses a completely passive system, uses fins for stability. This is something that we actually have to consider. We have to consider that this thing will be stable on the way up. But fortunately, fins and fin design are not the only thing that we can rely on when it comes to keeping a rocket stable in a situation like this. We also have something called spin stabilization. I'm not just clean off the blackboard to launch into this next part. Pun intended. The idea of spin stabilization. So you may see videos or footage of satellites being launched or launching or being deployed from the space shuttle, and have a little solid motor on the back, a nozzle out the back, and you have the satellite up here, and it'll be spinning. And there's a reason for that. It's because it just so happens that let me take a little step back. So some people try to think this is it's gyroscopic stabilization. It's you're pumping energy into this thing so it'll stay in the right orientation. But that's not entirely true. It's kind of the lies told children version because the real version is a little more messy. When you think about a rocket, it's a long, thin object, right? Like this pencil, a long, thin object. And when you're spin stabilizing a rocket, you're spinning it along the long axis really, 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 really fast. The problem is that that's not the point in which your pencil or your rocket is the most stable. It's actually along the long axis where you get your maximum moment of inertia. And your system will try to default to that in any way, shape, or form that it can. The reason why you spin it is because you are putting energy into it at its lowest moment of inertia in the system, and you set it up so that way there's no opportunity for the system to go, oh hey, let me just kick into this alternative orientation here. And this is a real thing that happened in spaceflight history. The first American satellite, Explorer 1, was kind of pencil-shaped. It was very long and thin. It weighed like 11 pounds. It was kind of tiny. But it was spun up to 750 RPM along that long axis. And when scientists were observing it, after the flight, they found that it was actually tumbling end over end at about 7.8 rotations per minute, a long way. And that's because it had little whip antennas on it, very long, thin wire antennas, and that served as a means that they were flexible for some of that energy to start dumping into that other orientation and for it to settle into that maximum moment of inertia. But it is resistant to coming out of that if you're not putting extra energy in the system and you're designing it smartly enough that you don't have little pathways for the system to go, oh, hey, let me just default to this more stable state. And that's part of the reason why you spin stabilize a rocket. It's harder to push this out of its I'm going to steal a concept from my background, which is a little bit of evolutionary morphology. But there's this concept of the adaptive landscape. Man, my professor did that so much better than I did. In which you can kind of treat it topographically. You have like islands of stability here and here, and it's kind of almost exactly like that for the moment of inertia thing. You have your lowest moment of inertia. You have to become unstable to become even more stable. So generally speaking, we'll stay in this island unless something comes along and pulls you down the hill and back up again. And that's part of the reason why you spin stabilize a rocket, because it is stable along that axis. And as long as you design it so you don't give it that pathway to go up that hill, that higher stability point, it won't. And there's a second reason why. That's because life is imperfect. You think about a rocket, it's a bad drawing of a rocket, my God. I cannot draw these things to save my life. You think about a rocket, it's got fins. It's got a body, a fuselage that's relatively aerodynamically symmetrical. You don't really think about it that much. There's nothing really wrong there. You may have little paint blebs or something like that that'll affect your aerodynamics, but not significantly. It's the fins and the engine are your two places of error. Because if your fin's off by like 1/10 of a degree, really, really hard to see, but still there, you have a little vector coming off of it that's a little skewed. And that means your rocket's going to start wanting to go off and do its own thing in that general direction. So by spinning it, you take that error and you average it out over a much larger area, and it kind of partially self-cancels. So you can constrain your error to much greater errors from build and design or what have you. You can constrain that more effectively if you have the ability to just kind of say, we're just going to average out across the whole thing and call it a day. Same with the motor, too. Not all engines burn symmetrically. And that's completely okay. You have to make the consideration that the engine may have little asymmetries in how the motor is running, and you have to plan for that. And by spinning it, you you average out that error across a much larger area, partially self-cancels, and that means you can have a much straighter and much more simulation-accurate flight. And that's a really nice and convenient thing. So for our considerations, of course, we're talking about basically building a rocket that is all solid, has no active stability on board, and launches off of a rail. And that means that you pre-program that spin into the fins. You take the fins, you actually angle them a degree or two. And as the air flows past it, it's asymmetrical, so it spins up. So it launches off the rail, and it starts spinning. And then it gets up to space, and it's still spinning. It's nice, it's stable, it's happy, it's living at that little energy state right there where it's not going to, it has something have to happen for it to pop up to that other higher energy state. Problem is that at some point you want to stop spinning. You've had this, if you're taking pictures of something and you're going like 760 rotations per minute, it's a little fast. I don't even know if even with the fastest shutter speed, the capturing is meaningful. So what you do is when you're in space, and you've probably heard of this before, you use conservation of angular momentum, you get little weights on cables, and you release the weights on the cables. And you immediately stop spinning, or at least slow down greatly. And this is from conservation of angular momentum. You think of the figure skater drawing her arms in to speed up and putting her arms out to slow down. Same principle, everything's conserved, but the advantage is you just fling these things out to the side and you slow down. You decrease your spin rate immediately. And this is called a yo-yo D-spin in actual parlance and in space science, and these are very common. In fact, they're so effective that you can go spinning really, really fast in one direction. If you set it up right, you can actually start slowly spinning in the other direction once the weights are deployed. And then what you can do is to shed that, all of that rotational energy, you can cut the cables and let them fling off into space, and that's that. You've slowed your thing down with an almost completely passive system. So, and this is in fact a really great way to do it. You spin up on the way up, and for doing stuff in space, you spin down once you're already safe. You chuck out your weights, and that's that. So that's really like a very high level look at aerodynamics when it comes to this, and I can of course go into far more detail about this because talk about nose cone shapes. I can talk about fin shapes and why they matter. But I think that for the purposes of this lecture series, this is a really good overview for saying, why do we do these things? Why do we spin stabilize? Why do we basically just a really a first level approximation. And I think that's a really good way to summarize it. There's one final topic that I have to get into, and I know that it's getting real. Chuck rolled off the damn table again. And I know that it's getting a little bit long here. I think we're coming up on an hour and a half of this. But there's one final thing I have to talk about, and that is basically the idea of building a reliable system. I forgot to erase the board. We'll do that. So that's fine. So the final thing I want to talk about in this lecture series for engineering considerations is the principle of reliability. And that seemed a little weird on the surface because this is almost exclusively dealing with probability and statistics. Where's my chalk? It just had there it is. This is almost exclusively dealing with the domain of probability and statistics, and that's a little less engineering than we're considering. But I want to introduce you to your least favorite friend, the product triangle. Not reliability. Pick two. That is what you must face. Any problem solving when it comes to engineering, you must pick two. And that is it. You cannot bargain for all three. You cannot find a way to get all three into your system. You will fail miserably if you do. You must pick two. And this is like where the rubber meets the road when it comes to dealing with engineering challenges, because you want all three. You really want all three to work. You want to be able to build something cheaply that's cost effective and works really, really well. But you can't. It's just a fundamental force of the universe that you cannot. Because your budget, your sanity, and the amount of hours in a day are all finite. So you have to start have to balance off of these three things. And in our consideration, we're dealing with an orbit-capable rocket. That's a system that inherently has to be extremely reliable. But it's also a system that we're building on a budget. And we ideally want to do this before we're old and gray. Oh no, we have to consider all three of these things. Whatever shall we do? And that is where some of the principles of probability and system design start rearing their ugly heads. Because we can't build a system that's perfectly reliable. We can't make something that functions perfectly every single time, especially because you have to consider the effort that's involved. When you think about it, getting something that works 50% of the time is pretty easy. Something that works 80% is a little more challenging, but not as bad. Something that works 100% of the time may damn well be impossible. The effort just goes off as an asymptote at 100, in that success range. So it's really hard to get a system that's perfectly reliable as a single unit. But there are tips and tricks that you can use. And some of these are from lessons learned from rocketeers throughout history. But I think the most important one to talk about is redundancy. Well, there's really two ways you can solve this problem. You can either have a system that's very redundant and will work even if parts of it are broken, or a system that is so simple that it's very hard to make it fail. And two different approaches, you bring them together in their own ways. They have their own advantages. You ideally want a system made of very simple parts that is also fault tolerant. And one of the first ways we can do this is we can come up with the Corium voting system that's used in a lot of guidance computers. So you can't trust one computer. You can get a computer that's, let's say, 90% reliable, and that's the best you can make it with what's available off the shelf, what you have on hand, and what have you. So what you do is you put it in a three-node system. And we'll call these nodes X, Y, and Z. That problem won't be relevant again, but I like labeling things. So you have three nodes. Each node is 90% reliable. How reliable is this whole system? How can you create an extremely reliable system out of this? Because there's a catch. The reason I say Corium voting is that if you're making a decision, you want to be able to trust that you get the right output. And the easiest way to do that is that you basically have three systems that are running in parallel that are voting on whether or not you're good, oh no, things are bad. And you're doing this constantly. And that means that you have a system that will work if all three nodes are functioning or if one node is broken. And you can control for that, not broken, but malfunctioning or not receiving the right data or what have you. You have the ability to say, yep, we're good, we can keep going. Versus making sure that at least one of them functions. But Corey voting is very popular in guidance systems for this exact reason. So the probability of this entire system working, and it's something that I had to relearn because I took probability statistics like 3 years ago. But the probability of this system functioning correctly, and you're going to have to bear with me here because I can't really walk the derivations, is the probability that all of them are successful to the third power plus 3 times the probability that one of them fails times the probability that exactly 2 of them are successful. And this looks a little weird. And you might say, well, why are you multiplying this? But what does any of this mean? What we're basically saying is that there's one way that every system works, that X is good, Y is good, and Z is good. It can only happen in one way. If we're asking for only one node to fail, then we have X can be bad, oh that looks weird, Y can be good, and Z can be good. Or it could be X could be good, Y could be bad, and Z could be good. Or it could be X could be bad, no, X could be good, Y could be good, and Z could be good. No, Z could be bad. So there's 3 different ways in which you can have one node fail. And this is true, you can have 3 different ways for 2 nodes failing, and only 1 way for all 3 nodes failing. So we can look at this probability space and we say, okay, this is a 10% chance of happening, this is a 90, this is 90, 90, 10, 90, 90, 90, 10. And the easiest way to rewrite that is just 3 times those probabilities, so they're all the same values, linked together like this. And what we find is that in a Corium voting system like this, where you need 2 nodes for them to function, just get an approval, green light, you're good to go for the rest of the flight, is, wow, that is not the right number, or 97%. That's pretty remarkable. That means that you have a guidance system based off of 3 nodes that have a 90% chance of working each. You have a guidance system that has a 97% chance of returning the right result, which is a huge increase in reliability. Again, I talked about the a little curve. It takes so much effort to get to that last 10%. Well, this is how you do it. You literally design a system that is built out of nodes you can actually achieve, and then you set it up in such a way that you get a feedback, and you can have a system that will function 97% of the time, even if one of those nodes is broken. And that's actually as good as having one node that works 97% of the time. And that is how you balance these 3 things in the product triangle, is that you basically substitute performance for fault tolerance, for redundancy. You build systems that are capable of working even when parts of them are broken. And to look at another example of this, let's say we're dealing with some kind of actuating surface, or we're dealing with a hinge, and we have a 3-part redundant hinge that's all designed to basically have the same output. So you look at this thing in the larger system, you can basically replace it with a black box that's 97% successful. That's great. But let's look at a slightly different scenario, where you only need one part of the system to function. Again, I can use like an actuator. I can use an actuating control surface or something to that effect as a starting point for this, because that's an easy way to have 3 nodes. So what we do is we have our little tree here. We have X, Y, and Z, and they're all coming out the other end. And we want to make sure, we want to figure out how reliable this is. Well, we have a system that is composed of nodes that are 90% effective. I use decimals, but now actually that's not even the right decimal. Wow, that's 9% effective. We don't really want that. We want 90% effective, because we can achieve that. We can see something that works from 1 to 10 times. And so the calculation of this is actually almost identical to the previous one, except now we can accept the fact that 2 nodes will fail. So the probability that all 3 nodes work is thus 8.9 cubed, plus the probability that 2 nodes work, which is 3, because it can happen in 3 different ways, times 0.1 times 0.9 squared, plus the final term in our equation that 2 nodes fail, 3 times 0.1 squared times 0.9. And what we find is that even though this system is composed of nodes that only work 1 time in 10, and again I stress that, and really think about how big 1 time in 10 is. That's like if you went out to your car in the span of every business day, it would not work one of those days. This system becomes 0.999 reliable. Pretty cool, huh? Which means you can build a system that, as long as you just want that output, you just have that input, you have a triple redundant system in there. With 90% reliable nodes, you can have a system that is as reliable as that very edge of that little effort curve without much effort. Because again, redundancy. It's very easy to build 3 parts of the system that are relatively low in reliability rating than it is to stress about making it 99.9% reliable part. And of course, the fewer moving parts you have, the better your system will be overall. You can think of it like an old car engine. Very simple systems, very easy to fix, very easy to diagnose, it's very easy to not break, because it's just so little that can go wrong with it. A very complex system will surprise you in new and creative ways of how it can go horribly wrong. So we think about this in one final application, which is what we talked about parallel redundancy. What about serial redundancy? Well, one event has to rely on the next, has to rely on the next. And that's kind of what we talked a little bit about with staging. And a good example of this is, let's say, a 3-stage system that is that it has each stage is 90% reliable. And that's all that is, then the whole system is just for a 3-stage rocket with each stage that is 90% reliable, you have a 73% chance of a successful flight. It's like 1 in 4. Actually, it's less than 1. It's less than 3 in 4. That means you will have a situation in which for every 4 you fly, 1 of them will fail. That's a huge number. It's incredible. No one would ever sign off on that kind of reliability. So when you're trying to solve a problem when it comes to something complicated like a rocket, you have to accept the fact that not everything will work. You have to design a system that will tolerate things not working. That's the only way that you can actually build a project that is cost effective in a reasonable time frame and on budget, by actually taking a very conservative and redundant and failure tolerant system. So I mean, yeah, that's the big engineering lesson for today, I suppose. So I think I've basically covered everything I wanted to cover for this lecture series. It's a pleasure having all of you here. I don't really have any bonus lecture topics unless there's something I think of in the next 2 seconds. But in the final one, we're going to talk about the historical context of engineering design decisions, and it'll be really fun. So I'll see you in the next one.